Now, Cayley-Hamilton theorem, it says a matrix satisfies its own characteristic equation. And this becomes very useful to find A inverse. This is a very important theorem to find A inverse without doing any of the adjoint A by det A or Gaussian elimination. Simply by algebra you can solve. So a matrix satisfies its own characteristic equation. That is the Cayley-Hamilton theorem. We will directly take an example and show this. Let A be 2 minus 1 1 minus 1 2 minus 1 1 minus 1 2. So it's a symmetric matrix. You can see it's a symmetric matrix. Question is, find the characteristic equation. Find the characteristic equation and show that A satisfies it. A satisfies the characteristic equation. Also, find A inverse. From the characteristic equation. Okay. So let us do this. So I'm not finding the eigenvalues, eigenvectors. We can do it, but directly the characteristic equation A minus lambda I equal to 0 determinant. This will give, see, this minus lambda I will only get reflected in the diagonal. All other elements remain the same. 2 minus lambda minus 1 minus 1 1 minus 1 2 minus lambda minus 1 1 minus 1 2 minus lambda equal to 0. So let us do this now. 2 minus lambda times 2 minus lambda the whole square minus 1. Minus of minus 1 is plus 1, the second term. The second element. So minus of minus 1 times, remove the first row, second column, minus 1 into 2 minus lambda, that is lambda minus 2, minus of minus 1, that is plus 1, plus 1 times 1, minus 1 into minus 1 is 1, minus 2 into minus of 2 minus lambda. So that will be plus lambda minus 2. So we get here lambda minus 2 the whole cube into minus 1. All right. And then plus lambda minus 2 plus lambda minus 1 plus lambda minus 1 equal to 0. So this is a minus b the whole cube is a cube minus 3ab square, no, 3a square b minus 3a square b, so 3 to 6 lambda square plus 3ab square, 3 into lambda into 4, so 12 lambda plus lambda cube, that is 8, plus 3 lambda minus 4 equal to 0. You multiply throughout by negative sign, lambda cube minus 6 lambda square plus 12 lambda minus 8 minus 3 lambda plus 4 equal to 0. Lambda cube minus 6 lambda square plus 9 lambda minus 4 equal to 0. So this is the characteristic equation. This is the characteristic equation. Okay. Lambda cube minus 6 lambda square plus 9 lambda minus 4 equal to 0. Now we have to show that this A satisfies this equation. That means instead of lambda, if you write A, then this should be satisfied. So only thing is here, instead of 4, you should get 4i. Okay. According to Cayley-Hamilton theorem, A must satisfy this equation. A cube minus 6a square plus 9a minus 4i. So let us do that. We know what is A. Calculation will be little because it is no zeros involved. It will be little. We'll have to do the calculation. So A square so A square is A into A. Let us do this. So this will be equal to so 4 plus 1 plus 1, 6. Then the first row multiplied by the second column, minus 2 minus 2 minus 1. So minus 2 minus 2 minus 4 minus 1 minus 5. Then the last one, 2 plus 1 plus 2, 5. Okay. Then second row, first column, minus 2 minus 2 minus 1. So minus 5. Then 1, 4, 1, 6. Then minus 1, minus 2, minus 2, minus 5. Then the last row multiplied with the first column, 2, 1, 2, 5. Minus 1, minus 2, minus 2, minus 5. 1, 1, 4, 6. So this is the A square. So A cube will be A square times A. So 6 minus 5, 5, minus 5, 6, minus 5, 5 minus 5, 6. This multiplied by 2 minus 1, 1. So a square multiplied by a, you will get a cube. So first row multiplied by the first column. 12 plus 5, 17 plus 5, 22. Okay, next. Minus 6, minus 10, minus 6, minus 10, minus 5. So minus 6 minus 10 is minus 16, minus 5 is minus 21. Next, 6 plus 5 plus 10, 21. Then based on this, we can again deduce minus 10, minus 6, minus 5, minus 21. Then 5 plus 12 plus 5, 22. Again, you can reduce here. You will get minus 21, minus 5, minus 6, minus 10, minus 21. Here you get 21, minus 21, 22. So this is a cube. Now we need to check. What we need to check? We will check the left-hand side. A cube minus 6a square plus 9a minus 4i. What is this equal to? A cube is 22 minus 21, 21, minus 21, 22, minus 21, minus 21, sorry, plus 21, minus 21, 22, minus 6 times a square, 6 minus 5, 5, minus 5, 6, minus 5, 5, minus 5, 6, plus 9 times a, 2, minus 1, 1, minus 1, 2, minus 1, 1, minus 2, 2, plus 4 times I, 1, 0, 0, 0, 1, 0, 0, 0, 1. So you cross check now. So this matrix remains as it is. This matrix remains as it is, a cube. You get minus 6 times of this. So you get minus 36. Okay. All right. Plus, I'm taking inside minus 36. 30 minus 30. 30 minus 36. 30 minus 30 plus 30 minus 36 plus 18 minus 9, 9 minus 9, 18 minus 9, 9 minus 9, 18, 400, 040, 004. So what do you get now? There is, oh, this is minus, by the way. This has to be minus. So this is minus 4, minus 4, minus 4. So now you can check. This should be 0. 22 minus 36 plus 18 minus 4. So minus 36 minus 4 is minus 40. 22 and 18 is 40. 0. Then minus 21 minus 9. Minus 21 minus 9 is minus 30. Plus 30, 0. Then 21 plus 9, 30, minus 30, last term 0. So you can cross check, you will get 0. So we have shown this, but matrix satisfies its own characteristic equation, that is Cayley-Hamilton theorem. All right. Now, because it satisfies its own characteristic equation, we can find inverse very easily. Okay, finding A inverse. Finding A inverse. So since A cube minus 6A square by Cayley-Hamilton theorem, 9A minus 4I equal to 0. This is by Cayley-Hamilton theorem. What we do, multiply by A inverse throughout. So when you multiply with A inverse throughout, what happens? A inverse into A cube becomes A square, because A inverse into A square. A inverse into A will be I times A square will be A square. Minus 6A plus 9I minus 4A inverse equal to 0. Got it? So we get 4 times A inverse is equal to A square minus 6A plus 9I. A inverse is 1 by 4 times A square minus 6A plus 9I. This is the easy way to find out A square, A inverse, without having to do inversion, determinant, adjoint, all those things. It is just simply one product and then addition of matrices, addition of scalar multiplier matrices. Now A square we calculated. A square is 6 minus 5, 5, minus 5, 6, minus 5. So 1 by 4 times 6 minus 5, 5, minus 5, 6, minus 5, 5, minus 5, 6. Okay. This and a bigger bracket. I'll finally divide by 4. Now this is minus 6 times A. 2 minus 1, 1. 2 minus 1, 1. A plus 9 times I. 1, 0, 0, 0, 1, 0, 0, 0, 1. Okay. So A inverse is equal to 4 times A inverse equal to, now you do the calculation. 6 minus 12 plus 9. So 6 minus 12 is minus 6 plus 9 is 3. Okay. Next, minus 5 plus 6. Minus 5 plus 6 is 1. And next is 0 anyway. Then the third term, 5 minus 6 is minus 1. And last term is 0. Minus 5 plus 6 is plus 1. Now 6 minus 12 plus 9. So again, the same 3 you get. And then again, here you will get 1 because minus 5 plus 6, 1. Then you get 5 minus 6 minus 1, 1, 3. So A inverse very easily we have found as 1 by 4 times this. So you get 3 upon 4, 1 upon 4, minus 1 upon 4, 1 upon 4, 3 upon 4, 1 upon 4, minus 1 upon 4, 1 upon 4, and 3 upon 4. This is A inverse found using Cayley-Hamilton theorem. Okay. All right. Okay. Now this is done. We have done most of it. For eigenvectors are called orthogonal. Just a few more points and then we are done. Eigenvectors are orthogonal if their dot product is 0. How is dot product defined? In vectors we know, right, how dot product is defined. So let's say x1 is x1, x2, x3. This is one eigenvector, and x2 is y1, y2, y3. So dot product is defined as x1 transpose x2. So this will be a column matrix, becomes a row matrix multiplied by the column matrix. So this will be a single entity, that is x1 y1 plus x2 y2 plus x3 y3 is equal to 0. So orthogonal eigenvectors means the product of their sum of the products of their corresponding elements will be 0. Okay, so that is one. Now the last of it, important concept, diagonalization. Diagonalization of a matrix. That means converting a matrix into a diagonal matrix. This is a diagonalization of a matrix. Sometimes pronounced as S can be written by Z also in some cases. Now, so for every matrix A, we can find a matrix D for a matrix A, we can find a matrix D, a diagonal matrix, such that A is M inverse D times M. Okay, D is a diagonal matrix. Now, what is M? This is of order n. It's a square matrix of order n. This is of order n by n. Diagonal matrix is also of order n by n. And M is also n by n. M inverse is also n by n. Okay. So we have converted A to a diagonal matrix pre-multiplied by M inverse and post-multiplied by n. Now, what is M? M is an n by n matrix whose columns are the eigenvectors of A. Whose columns are eigenvectors of A. All right. So if M are eigenvectors of A, you take the transpose, M first column is the first eigenvector, second column is the second eigenvector, third column is the third eigenvector. All right. And we will see what we get D as. So now condition for the matrix to be diagonalizable. Condition for a matrix to be diagonalizable. That means, will we be able to diagonalize the matrix A? All right. For that, the first condition is the matrix A must have n linearly independent eigenvectors. Only then it is possible, otherwise it is not possible. If linearly independent eigenvectors are there, then M will not be singular. Otherwise, M will become singular and M inverse cannot exist. So, matrix A must have n linearly independent eigenvectors. Second, okay. The matrix must have n linearly independent eigenvalues. The first condition is necessary and sufficient. Second condition is sufficient. A matrix must have n distinct eigenvalues. All right. So, of course, see, if there are n distinct eigenvalues, then for them you get n linearly independent eigenvectors. But other way it is not true. If they are linearly independent eigenvectors, it need not be true that all eigenvalues are distinct. So this is about diagonalizable. This is used in finite element method for solving complex equations, differential equations, and other in the final element method. We use this concept of diagonalization there. But this is a concept we need to learn. This much is sufficient for matrices.